Where we are in our discussion on linear regression is that we've seen how to build a multiple linear regression model. We've systematically done that by building it up from simple linear regression, incorporating both categorical and numerical variables into a multiple linear regression. And then what we did is we asked ourselves, is this model that we are building any good? And the way we did that is that we calculated performance metrics like root mean squared error, mean absolute error, mean absolute percentage error, R square and adjusted R square. And we calculated these based on two kinds of data sets or two data sets. One is a training data set and one is a test data set. Performance on the test data set, good performance on the test data set implies that the model is going to work well on unseen data, data that it has not been trained on and data that it will see later when it is in a runtime environment. So we can summarize all of this by simply looking at a model comparison table or a model comparison metric. And what we're going to do here is look at all these models and we're going to see which model to some extent worked well or not. By some extent, what I mean is not all the models have performed well. So what we're going to do is we're going to create a data frame, and this data frame is going to concatenate all these performance measures. And these performance measures were rows in my previous analysis. I want them to be columns now so that I can look at all the models as rows and all the performance measures as columns. So therefore, I will take a transpose of them simply for visualizing to see whether these models correspond to what we think they are. I'm also going to write down what the models were: sales versus advertising, sales versus discount price, product price, the full range of multiple linear regressions ending with sales and all independent variables. So now, if I run this, which is simply generating a table of numbers that I've already seen, here is what I get. So let's take a look at this table and use it to summarize what we have learned. First, simple linear regression. Simple linear regression can actually work quite well if there is a variable that is correlated with the output. In this case, advertising expenditure was correlated with the output. By correlation, I mean a positive correlation of some magnitude, where we got an R square of about 41%. An R square of 0.41, I'm reporting as an R square of 41%. I know I've been using this language interchangeably, but if you wish, you can stick to saying R square is 0.41. An R square of 41% only from sales, which corresponds to a mean absolute percentage error of about 9.64. Now, all this is on the training set. This entire thing is on the training set. This R square of 41% is going to be lower if the simple linear regressions are not from variables that are highly correlated. To include those variables in a model, we can add them to a model that has highly correlated base variables to begin with. Add them to, for example, to sales. And as you can see, even if I add a variable like discount percentage, which is not a good variable, my R square did not increase much. In fact, its increase was only in the 6th decimal place, which means discount percentage added on to advertising essentially did nothing to my model. And you can see that same effect in my MAP. My 9.64% remained 9.64%. These are often good indicators when you try to understand whether discount percentage is a key lever for influencing sales. And the answer seems clear. If you're advertising and that budget is in your control, playing around with discounts separately isn't going to give you an additional lift. That's the learning from the model, so to speak. That's the learning that has come from the data. That doesn't mean that you cannot get a lift in your R square and you cannot get a corresponding drop in your MAP by adding other variables as well. So for example, with price, I know that my R square has now gone up to 0.637. Despite the fact that price itself may not be very significant, but it is adding additional information that discount percentage did not. Discount percentage is associated with advertising. So it's not adding much to a model when advertising is already there. Product price, despite not necessarily giving an R square on its own, is increasing it simply because the information that it gives is separate from the information on advertising. You could argue that way. Or you may choose not to argue this way at all. Maybe you think this is spinning wheels. But just look at the numbers. R square is 0.63 and now my RMSE has gone down from the range of things like 2,700 to 2,100. By adding a variable like popularity, I can now increase that to 0.66 or 66%. By adding all variables, my R square can go up to 70%. My MAP can come down to 6.7%. My RMSE can come down to less than 2,000. My MAE, which is comparable to my RMSE, except that I do not square and take square roots, follows a very similar trajectory to my RMSE, except that the scale is slightly different. There's no squaring going on, but you see that the MAP sort of tracks the RMSE with respect to saying which model is better than the other. Adjusted R square is only going to make a difference from R square when the model is very big, and at the scale of models that we're looking at, these are not very big. So adjusted R square will only make sense in the sense that it will give you new information that R square is not when you have maybe 50, 60 or 100 up variables. All this on the training set. Is this performance holding up on the test set? So if I now go back and I repeat this on the test performance data. So now I'm concatenating all my test performance numbers as before. And as we had already seen, the performance there was not bad. So does this model generalize well? To see that, we need to see performance on the test set. On the test set, our numbers are going to look a little different. But will they look substantially different? Let's not go into all the numbers at this point in time, but simply look at what happened to our final model. And let's see that in the final model, I again have an R square of about 0.72%, and more importantly, an MAP of 6.73% or 6.76% and an RMSE of 19.07, which are very comparable to the model's performance metrics that I got on the training set. And so therefore, this model is showing comparable performance on the test set and the training set. These are the two metrics, or these are the two ways of thinking that people use in machine learning. And let me reiterate that as we come to the end of this. Good performance on the test set, number one. Number two, performance on the test set that is close to performance on the training set. Good performance on the test set means the model is predicting well. Good performance in the sense of low difference between training set and test set means the model is generalizing well. So it can stay alive in the field, provided nothing substantially changes in your business environment. It can stay alive longer. Both of these things are very important in machine learning. Is the model good? And does the model work well in newer data sets or in the future? Are we okay here? We're at over 70%. In a business setting, perhaps so. In other settings, your domain will tell you as to what is a good RMSE and what is a good R square and what is a good MAP. You need to think amongst yourselves. Figure out what it means in practice to be about 7% off on your sales forecast. Because that's what this means. You have to say that if I am off by 6%, 7% on my sales forecast, what are the implications of that? What if I underestimate by 6% or overestimate by 7%? Work through that and see, therefore, is this model good enough or not? And so, put the model to practical sense, so to speak, in addition to statistically meaningful results. and that will give you good outcomes. For now, we know that the final model of all independent variables exhibits the best performance. No surprise, all the variables are in there. The question is it good enough? And that's where the business part comes in. We've also identified certain things that are driving my output. I know that advertising is a good predictor of sales. I know that when combined with advertising, other variables are perhaps not that good. It seems to carry most of the information. I know that my categorical variables, particularly my popularity measure, is giving me certain lifts. So all these findings on key drivers are also there. Which variables are important? And you come away with a sense that I need to advertise better. Promotions should be about advertising, perhaps less so about discounts. I need to make my product popular over and above whether it advertises well or not. And if I build a good model, and maybe I build a more sophisticated model, maybe I build a more sophisticated model like AI model, like what people do in artificial intelligence, like a neural network model, etc., etc. I should at least expect maybe a 6% MAP and probably a lot less than that. Because even assuming the limitations of a simple linear regression model, I have been able to explain less than 7, I have an error, or I'm within about 7% of my actuals on new data sets. An AI model should at least do better than this. But linear regression is a start to supervised learning. Use it to get key drivers, understand variables. Also use it to get an assessment as to how well you can predict. And then, from there, if you wish, expand out to other models. But it is a terrific place to start and a great place to begin analyzing data and set benchmark models for machine learning and even more sophisticated AI algorithms. In conclusion, let me summarize what we did. We looked at data. We said from this data, I'm going to identify a column that I want to predict. Once we have identified that, we played 2 tricks on the data. The first trick is making sure that the data is correct column by column. We did that for categorical data by doing encoding. The second trick we did is we divided all the rows of data into 2. One on which we built the model and one on which we tested the model. Train and test. So once we've identified the Y, once we've modified my X's, made them numerical, once we've identified test and train, we built a series of models. And those models allowed me to evaluate regression both from the context of prediction and from the context of explanation. My 2 major objectives of regression, to predict and to understand. Putting together what you saw in this Python notebook and what you've seen in the conceptual part of the material that you're seeing, you should now be in a position to be able to take a business problem, to identify variables, to figure out what a linear regression model should look like, get the data, process the data in the way we just discussed, and then build a series of models, see which model is good, take that model, work it back to the business problem, see what it tells you about the business problem, and then use it for prediction in the way that you want to. Try this out on your own data sets and see whether you get good understanding of your business or better understanding that you had, and see whether it gives you a good predictive machine learning algorithm to begin your journey in that direction.